Okay, so this is our next section, 2.6, rational functions now. These are a little more interesting. And first things first, the domain of these guys. So the playing field, so to speak. The objects we're looking at look like this. They'll be ratios of polynomial terms. Okay, so some polynomial p of x over some polynomial q of x. And the domain will be all real numbers except where the denominator is equal to 0. So all real numbers except where q of x is equal to 0. Okay, so let's take a look at number 6 in the book. And I probably want us to figure out the domain. So I have h of x equals x plus 8 all over x squared minus 64. Okay. So what I'm going to do is factor the denominator x minus 8 times x plus 8. And I'm setting it equal to 0. So x minus 8 equals 0, 0 factor property, x plus 8 equals 0. So x equals 8 or x equals negative 8 are our restricted values. So at the end of the day, the domain, all real numbers except those guys. So negative infinity to negative 8, union negative 8 to 8, and then union with 8 to infinity. Okay. In order to talk about the end behavior of these graphs and also later about asymptotes, we need some special notation now. So this is arrow notation. And you'll see this in calculus if you keep taking math. So first off, x going to a from the right. So you do a little exponent like that to indicate you're coming in from the right. So we have a, and then I'm considering the approach from that direction. Approaching a from the left. So again, I guess we should think of this as the x-axis. We have the x-axis, and we have some value a on the x-axis, and we're considering this approach. X going to infinity. Okay, so again, we have the x-axis here. And what we mean by this is we're just looking at what happens as we go farther and farther out on the x-axis. And then likewise, as you go to negative infinity, you're thinking about going forever and ever in the other direction on the x-axis. Okay, so to make this a little more clear, let's take a look at the problem they have in the book. So page 398. And they give us a nice graph. Three tick marks there, about 2 tick marks on the y-axis in each direction. And then it looks like this here, and like this here. So they have asymptotes at -3 and at 1. And then we have this graph here in the middle. And we have this graph over here. And finally, we have this graph over here. Okay, so we'll go through some of the exercises then. Number 9, as x goes to -3 from the left, we want to know what the y values are doing. In other words, f of x, the associated y values go where? Okay, so go blank. Right, so we take a look at the graph as x goes to -3. So where is -3? There's -3 here, it's -2, -1, 1, -2, 1, 2, 1, 2, 3. So I'm coming into -3 from the left, and I want to know what the corresponding y values are doing as x goes to -3. Okay. So the y values seem to be going to -infinity. It's going down, 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 and just keeps on going down and down forever. Okay. So one way to think of it is kind of like you have something you're controlling, like a mouse, and then you have an arrow on the screen, right? And you move your mouse around and the arrow moves around on the screen. You want to know how the arrow on the screen is behaving as you move that mouse around. So imagine you're out of sync or something, and you're moving that mouse, and your arrow on the screen is just jumping all over the place. Okay, maybe that's an issue. You want to be able to describe that issue, and the way we chose to do it is to say as x, so you can think of that as your mouse goes to -3. So I'm moving my mouse here, and on the screen, maybe the little finger pointing or whatever they have on the screen is going down, 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 down. So as I move in this direction, the thing on the screen is going straight down. And that's kind of what we're after here. Okay, number 10. As x goes to -3 from the right, f of x goes where? Okay, so this time I'm coming in from this direction, or I'm moving my mouse in this direction, and then the arrow on the screen is just flying up, straight up into the air as I get closer and closer to -3. This thing is going higher and higher up. Okay? You have to use your imagination a little bit once you get closer and closer. So if it goes up and up and up and up and up, we'll say that's going to infinity. 13. As x goes to -infinity, where does f of x go? So going to -infinity, x, you're going in this direction, and here the y is going like this, and then it sort of jumps over to here, and then they're sort of at the same place. So as the x values go to infinity, the y values, so you're measuring where the y is using this axis, the y values are going to 0, actually. So back here, they're way maybe at 10, -3, -2, -1, 0, getting really close to 0, so 0. Excuse me. 14, as x goes to probably positive infinity, then f of x goes, the y values go where? Okay. So in this case, you're thinking this direction, right? So you maybe start out at 2, 3, 4, 5, 6, 7, and it looks like the height values are going to 0 as well. Okay, these vertical lines here at -3 and 1, we're calling those things vertical asymptotes. And you'll have these things when the numerator is not 0, but the denominator is. Okay, so section 3, finding these vertical asymptotes is our task. And again, we're given this rational function, we call it r of x, equals p of x over q of x. So again, it's a ratio of polynomials. We'll have a vertical asymptote at x values where g of x, or rather p of x is not 0 and q of x is 0. Okay. So if they're simultaneously 0, it turns out there's going to be a little hole in the graph at that point. Okay. Okay. So let's look at an example here. We have example 2. part A, f of x equals x over x squared minus 9. You'll split this process into two parts. First, find out where the numerator is equal to 0. So we have p of x is equal to x, right? And so p of x is equal to 0 when x is 0. Find where q of x is equal to 0. So q of x is equal to the x squared minus 9 part. Set that equal to 0. And we have 3 and negative 3. Right? So at 3 and negative 3, the denominator is 0 and the numerator is not. So this is a good thing. We'll have the vertical, well, I mean, for what we're doing, it's a good thing. The vertical asymptotes will be at these places. Okay, vertical asymptotes at x equals 3 and negative 3. So if I had 0 over here as well, then there wouldn't be a vertical asymptote there because there would be a 0 here and a 0 here. Okay, so in part B, we'll see that issue play out. Part B, we have f of x as our function. The name of the function, x plus 3 all over x squared minus 9. Okay. So in this case, first take the numerator and set it equal to 0, x plus 3 equals 0. So p of x will equal 0 at negative 3. And then secondly, x squared minus 9 equals 0. So we'll have x minus 3 times x plus 3 equals 0. So x will equal 3 or negative 3. And there's an issue, right? So at negative 3, there will not be an asymptote, there will be a hole. But at x equals 3, there will be a vertical asymptote. So vertical asymptote at x equals negative 3. And then there's going to be a hole at x equals 3, but the particular point will be 3 comma 1 all over, sorry, where's the hole at? Negative 3. So there's a sorry, I screwed the pooch on that one. At x equals 3, there's a vertical asymptote, but at negative 3, there's a hole, and in particular, it's negative 3, comma, negative, so it's going to be, yeah, negative 1 all over 6. So how did I figure out the y coordinates? It's from looking at the original function. You can rewrite this as x plus 3 all over x minus 3 times x plus 3, and then reduce, so long as you presume that x can't be equal to negative 3. Okay? If you presume that, you can reduce this into 1 over x minus 3, and then you could plug negative 3 into this formula here, and you'll get negative 1/6. Okay? So you can only do this, though, if you put that hole in the graph. Otherwise, so if you say x can't be negative 3, you can do this simplification. But otherwise, you're not going to be able to do that. If you try to put negative 3 into this equation, you get 0 over 0. Okay, so we don't really know what to do with that just yet. But yeah, sort of do now. So anyways, let's take a look at what this thing looks like. We should be able to graph it kind of just using our notions of fundamental graphs. Whoops. So the fundamental graph we're doing is a rational function. It looks like this. This was the graph of y equals 1 over x. And then this character here, 1 over x minus 3, is just a shifted version of this, right? It shifts it over 3 places, 1, 2, 3. That's actually where the asymptote will be. Okay? And then we'll have at negative 3 a hole. So I have to be a little careful about that. So negative 3, negative 1/6, there's going to be a hole in there. But otherwise, it's exactly the same as one of these, just shifted. Okay? Okay, so a vertical asymptote there at 3. Okay, not finished. Right? There's a lot to do in this section. In addition to vertical asymptotes, there's actually horizontal asymptotes, we should think of not as much as an asymptote, where I think a lot of people think the vertical asymptotes, um, I mean, horizontal asymptotes aren't the same as vertical asymptotes because you can't really cross a vertical asymptote. Horizontal, turn on the right and think at the same time. Okay. You can actually cross horizontal asymptotes, and what these things really are just sort of they tell you what the end behavior is. So we're talking about the end behavior of the graph. In other words, what happens as x goes to infinity or x goes to negative infinity. Okay. So, right, an example of this phenomena, let's say I have, and this will be our horizontal asymptote right here, maybe there's a vertical guy right here. I have this kind of behavior. Okay. So as x goes to infinity, the y values are getting really, really close to 1. As x goes to negative infinity, the y values are getting really, really close to 1 as well. So we'll say there's a horizontal asymptote when this happens. Okay. Identifying these horizontal asymptotes is a problem you'll revisit in calculus, but for now we kind of have a way of figuring these out. By looking at the degrees of the numerator and the denominator. Right? So locating horizontal asymptotes. So first case, the degree of your numerator is less than the degree of your denominator. In this case, you'll have a horizontal asymptote at y equals 0. Okay. The second case is when the degrees of the numerator and denominator are the same. And what will that imply? That implies y equals the horizontal asymptote equals the ratio of the leading coefficients of the polynomials. So I'll just write a sub n over b sub n. Or maybe I should make that more clear. Ratio of leading coefficients. Okay, the third case then, we have the degree of the numerator is greater than the degree of the denominator. In that case, you won't have your traditional asymptote. Okay, there may be a slant asymptote though, right? So we'll just say for now none, and then maybe later worry about slant asymptotes. Okay, let's take a peek at this process. So checkpoint 3. Part A, we have f of x equaling 9x squared all over 3x squared plus 1. Okay. So looking at this, the degree of the numerator is 2. The degree of the denominator is also 2. So what? That means you take the ratio of the leading coefficients. So here's the numerator's leading coefficient, and here's the denominator's leading coefficient. And that'll be your horizontal asymptote. Okay, so y equals 9/3, which of course is just 3. Part B, so like that, we have g of x now equals 9x over 3x squared plus 1. Okay, so this time the degree of the numerator is 1, the degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator. That means automatically your horizontal asymptote is at 0. Thirdly then, h of x, what's the deal here? We have 9x cubed over 3x squared plus 1. This time the numerator's degree exceeds the denominator. So that tells me there's no horizontal asymptote. Whoa, okay, so I guess we're going to graph these now. We'll put all this material together and let's talk about the sort of process. So section 5, graphing. There's 7 basic steps you want to do. First, even oddness. Right? Secondly, get the x and y intercepts. Thirdly, get your horizontal vertical asymptotes. And note if there's any holes there. Fourthly, they want you to plot some extra points to help you out. And then, of course, lastly, graph the thing. Okay, so let's go at it. This will be checkpoint 5. We have f of x equaling 3x minus 3 over x minus 2. First, even oddness. So I'm replacing x with negative x. I get 3 times negative x minus 3 all over negative x minus 2. This is going to have sort of opposite signs. I mean, if you put in a negative up here, it wouldn't even work out for you. So right now you have negative 3x minus 3 all over negative x minus 2, which is certainly not this original guy. The only hope is maybe you can factor out a negative, but still that isn't going to work either. You factor out a negative from the numerator, you're going to get 3x plus 3 all over negative x minus 2. And clearly that's not this with a negative in front of it, you know. The denominator has flip-flopped. This is negative instead of being positive, but this is the same. Up here you have, this is positive instead of negative, so it's not the same thing. And there's no way to remedy it. Okay, so secondly then, let's get our x and y intercepts. So for the x-intercept, you let y equal 0. And essentially all you're doing is setting the numerator equal to 0 if you wish. Well, let's do it in all of its glory. So we're assuming x can't be 2 in our solution. Okay, so x equals 1. For the y-intercept, you let x equal 0. So we'll have y equals negative 3 over negative 2. In other words, 3 halves. Okay, all right, so there's that. I need the horizontal and vertical asymptotes. So for the horizontal asymptotes, the numerator and the denominators. All right, so we have to look at 3x minus 3 equals 0. And so x minus 1 is 0, so x is 1. What we're doing there is just making sure we don't have one of those holes. So the denominator, x minus 2, so x is 2. Sorry, this is the vertical asymptote. Okay. So there will be a vertical asymptote at x equals 2. If this was 2 as well, then there would be the hole. Okay. For the horizontal asymptote, all you're doing is then looking at the degrees of the numerator and denominator. In this case, they're the same, so you just take the ratio of the leading coefficients. In the numerator, the leading coefficient is 3. In the denominator, the leading coefficient is 1. Okay, so you'll have 3 over y equals 3 as your horizontal asymptote. Okay, let's get it sort of started. We can plot the x-intercept at x equals 1. There's a y-intercept at 3 halves. There's a vertical asymptote at x equals 2. And then there's going to be a horizontal asymptote when y is 3. And you probably want to get a couple extra points now. So X, Y on our graph. I picked something out in this direction so I can sort of get an idea of the behavior in that direction. So I tried X equals -4, and it should be going to 3 in this direction. Okay. I also want to see what's happening in here. So you could pick something like negative or positive 1.5. And then you're going to want to see what's happening in this direction. So you probably want to pick a couple over here on this side. So 3 and 5. And I went ahead and put those into my calculator earlier. It's just 2.5, -3, 6, and 4. Okay. So at -4, I have 2.5, 1, 2.5. And it's kind of going to have that be what I expect. So it's going to get the y values get super close to 3 in that direction. And then at 1.5, it's -3. Okay, so in this direction, it seems to be going to -infinity as we approach the asymptote. And then at 1, 2, 3, I'm getting 6. So I'm actually way up here. 6. And then at 1, 2, 3, 4, 5, it drops down to 4. Okay, so it's down to here now. And it'll have this behavior. Okay, so the one issue I didn't talk about was the slant asymptote issue, and that's when the degree of the numerator exceeds the degree of the denominator. So let's take a quick look at that. This is section 6. Okay, so instead of having a horizontal asymptote like this, we'll have something like this. And how do I figure out that slant asymptote? You'll have to do long division or synthetic division, whichever one you prefer. Okay. So problem 84, we have f of x equaling x squared plus 4 all over x. Okay. So we'll go after that slant asymptote. I'm going to have to do long division. So x into x squared plus 4. So x, what times x is x squared? So x times x is x squared. And then subtract. So you can bring down -4. And then that's it. So this will equal x minus, or rather plus 4 over x. This would just be plus. I guess I could have just butterflied that. Sorry, didn't need all that business. The slant asymptote will be this guy, this term right here. Okay? You just sort of neglect the fractional part and pick this guy up as your slant asymptote. Okay. Let's look at another one. So 87, how instructive that one was. We'll do this in all of its glory. So we're going to actually plot the thing. So 87, we have negative x cubed. So this is some function f of x equals negative x cubed plus 1 all over x squared minus 2x. And we'll get the slant asymptote first. Okay, so negative x cubed plus 0x squared plus 0x plus 1, and we're dividing by x squared minus 2x plus 0 if you want. So anyways, negative x times x squared is negative x cubed. Subtract them. 0 minus 2x squared. Bring down the next term. Negative 2 times that thing, so negative 2x squared plus 4x. Subtract them. Bring down the next term. And then that's it. So you'll do this kind of deal. And did I screw up there? Seems like, Yeah, I did. There's no There's no negative. So let me try that again. Yeah, I need a piece of paper. So 87. I copied the thing wrong. F of x is x cubed plus 1 all over x squared plus 2x. Okay, so again, I want to get the slant asymptote, so I'm going x cubed plus 0x squared plus 0x plus 1. The outside I have x squared plus 2x. So what times x squared is x cubed? So x cubed, x times x squared is x cubed. X times 2x is 2x squared. Okay, so subtract those, you know, negative 2x squared. Bring down the next guy. So what times x squared is negative 2x squared? So you go negative 2. So negative 2x squared minus 4x. Subtract. Bring down the next term. So that'll be 4x. Bring down the 1. What did I do this time? It seems like I screwed it up again. Oh, I screwed up my notes. There's a mistake in my notes. Okay, so anyways, your end answer is going to be this character here. So this guy will equal x minus 2 plus 4x plus 1 all over x squared plus 2x. And in particular, then, your slant asymptote is this guy right here. Okay. Right, so slant asymptote y equals x minus 2. Okay, so we have that part of the business taken care of. We need to go through and do our information. So first, is it odd or even? So plug in negative x into the original. You end up with negative x cubed plus 1 all over negative x squared is just x squared. And then minus 2x. So 2 times negative x is minus 2x. You can factor out a negative from the numerator if you really wanted. So you'd have x cubed minus 1 all over x squared minus 2x. Okay, this version is definitely not the same as this guy up here. Okay? And there's no way to remedy it. You can try to factor out a negative from the denominator. You'll end up with negative x squared down here plus 2x. So there's just no way to fix it. With the negative included, this thing is not the same as this thing. Okay? And you could try to factor out a negative from the numerator and make this numerator the same as this numerator, but it ain't going to work because you're going to end up with x cubed minus 1 instead of x cubed plus 1. Okay? So in my opinion, this thing is neither. Okay, so neither. Let's get the y-intercept. So 2 xint. You're letting y equal 0. So you have 0 equals x cubed plus 1 all over x squared plus 2x. Cross multiply. We got to avoid 0 and negative 2 as solutions. Okay? But we're going to end up with plus or minus 1, right? Or negative 1. So x cubed plus 1 is 0. So x cubed is negative 1. And then you take the cube root of negative 1, it's just negative 1. So y-intercept, in this case, let x equal 0. There isn't one. The denominator is equal to 0 at that point. So we'll write none. There's an asymptote right there. When x is 0, there's an asymptote. So it's not going to go through that place. Okay, so let's get the horizontal and vertical asymptote. So first the vertical, like I was saying, there's going to be, if you take the denominator and set it equal to 0. Oops, and I'm freaking playing around with this. It's not the right equation. It's this equation up here. So sorry, in a bit of a hurry. I got to go somewhere. So this guy up here we're playing around with for the vertical asymptote. You're looking at x squared plus 2x equals 0. Right? So factor x times x plus 2 is 0, so x is 0 or negative 2. So those will be our vertical asymptotes. Note the numerator is not 0 at either of those places. Here's where the numerator is equal to 0. It's at negative 1. So we don't have to worry about a hole, is what I'm saying. The horizontal asymptote, then the numerator is greater than the denominator. So there's no horizontal asymptote, but there is a slant asymptote. Okay, so maybe we should say slant and then put y equals x minus 2 down. And what else? So we need maybe some extra points eventually. Okay, let's start by graphing this thing. I'm going to try to squeeze it in over here. So I'll have a vertical asymptote right on the y-axis. I have a horizontal or a slant asymptote at y equals x minus 2. So at minus 2, there's an intercept and up 1 over 1, right? So we can draw a dashed line right there. Hopefully that'll be enough room. What else? Where's our vertical asymptote? So there's one at 0. We got that one. There's one at negative 2. Put that one there. Okay. And then our intercepts. So there's one at negative 1. It's right here. There's no y-intercept. So it's not going through this thing here, which is a bit odd. That would happen. But it happens. Is that I'm looking for other. That's about it. So I guess we're going to have to satisfy ourselves with a big table of values in order to get the job done. So what do you want to do? You want to pick some values over here on this side of the asymptote. You want to pick some values in here. You want to pick some values over here. Okay? And just because I'm in a hurry, the end result will be like this. And then over here, we'll have this guy. Okay, so a little bit different of a figure than what you're used to, but that's the deal. That's the dealio. All right, so you're probably going to want to try to plot some points to make that work out for you. -5, -3, -1.5, -0.5, 1, 2, 3, and 4, and that'll get you this picture pretty much. It'll give you the scaffolding for that picture. Should I do that? Probably. Let's see how I am on time. I got to get going. Okay, that's it.